This is a test to distinguish primary and secondary alcohols from tertiary alcohols. It uses the principle of oxidation. On the left here, I have the primary alcohol, propan-1-ol. In the middle, I have the secondary alcohol, propan-2-ol, a position isomer of the first one. And here to right, I have 2-methyl-propan-2-ol, a tertiary alcohol. So 3 colourless liquids. I need a hot water bath for this experiment. And what I'm doing here is carrying out a redox reaction. So here I've got acidified potassium dichromate, orange crystals dissolved in water, and dilute sulfuric acid added. There at the bottom you have the half equation showing that dichromate ions in the presence of acid H+ can take in 6 moles of electrons per mole of dichromate. It is in its orange +6 oxidation state to the left and its dark green +3 oxidation state to the right. So I'm adding acidified potassium dichromate here to the primary alcohol, propan-1-ol. I'll use a rubber bung to give it a good shake and then place it into a hot water bath. Let's consider the structure of propan-1-ol, and in particular we take a look at the carbon to which the functional group OH is attached. This carbon here. What you find then is if that carbon that's attached to the OH is also attached to at least one H atom directly, and this one here is attached to 2 directly, then it will undergo oxidation. And as a result, it will reduce the dichromate ions from that orange color to a dark green color. So the dichromate ions are behaving as an oxidizing agent, which means they themselves are reduced. So here I've now got the secondary alcohol, propan-2-ol, a position isomer of the first. I've added acidified potassium dichromate, and using a separate rubber bung to avoid contamination I've given it a shake, and into the hot water bath. And here's its structure, and there's the key carbon in question, the one that's holding the functional group OH, and you can see that it is too attached to one H below there. So the secondary alcohol should also undergo oxidation, so in turn that means it will reduce the orange dichromate ions to the +3 oxidation state, which is dark green. And then I'm taking 2-methyl-propan-2-ol here, which is a tertiary alcohol. Same procedure, adding acidified potassium dichromate, again to avoid contamination using a separate rubber bung. I'll give it a good shake. Although the alcohol is miscible with water and therefore miscible with the aqueous solution of dichromate ions. And into the hot water bath. So let's look at the key carbon, this one. It's holding the functional group OH. And here, very importantly, you can see that that carbon is not attached directly to any H atoms, and as a result will not undergo oxidation. So I expect that this chemical, propan-2-ol, will not reduce the acidified potassium dichromate. So there you have them in the hot water baths, and I'll speed up what took probably somewhere between 7 and 10 minutes. So propan-1-ol on the left, a primary alcohol, in the middle propan-2-ol, a secondary alcohol, and on the right 2-methyl-propan-2-ol, a tertiary alcohol, mixed with acidified potassium dichromate and placed in a hot water bath. Just topping up the hot water bath here. And again, I have speeded this up probably about ×4. You can see that something's happening in the first and second test tubes. The dichromate is changing color, heading towards that dark green color. So already we can see a positive test, so to speak, for propan-1-ol and propan-2-ol. They do reduce acidified potassium dichromate from its orange +6 oxidation state to its dark green +3 oxidation state. We cannot, and I would emphasize that, we cannot use this test to distinguish between a primary and a secondary alcohol, as they both behave the same, reducing the dichromate. But we can use this test to distinguish between a tertiary alcohol and both primary and secondary alcohols. So all that I need to do is leave it for a little while longer till we head a bit more towards that dark green color. Of course, if you've got green and orange mixed together, the color's somewhere in between. But now here, after probably 7 to 10 minutes, certainly at the top there, you see signs of that dark green color being produced. So in the case of the primary alcohol, which I've got here, we can see that the dichromate ions have been reduced from orange +6 oxidation state to the dark green +3 oxidation state. Sorry, I think that might have been the one in the middle. But the one in the middle and the one to the left both behave the same. Orange to dark green. And here's the result with the tertiary alcohol, 2-methyl-propan-2-ol. It has remained orange in color. The dichromate ions have not been reduced. And the reason why: the carbon to which the functional group OH is attached does not have any H atoms directly attached to it. Thanks for listening.